All right, so the idea yesterday was this idea of the area function. So like this is problem number 2, right? So again, let's investigate the different parts of this area function so we understand the notation. I don't want you to get lost in the notation of what's going on. This is little f right in here. It's probably good enough to just call that little f. It's f of t when it's inside there, but we can think of it as just, right, y equals x, right? That's the function, that's little f. When we think of the chart with what we realize, since it ended up being antiderivative, now we're going to spend one more day, and you guys are going to spend some time doing these areas, and like the one I did yesterday, we'll go through another one today, and so you're going to spend some time doing that. Now, in the long run, that's not going to be something you'll do a lot of, right? I mean, it's kind of like the long way of doing the derivative, f of x plus h minus f of x all over h, right? We spent some time doing that. Conceptually, the idea is slope between 2 points. The 2 points get really close together. That's the derivative, right? And we want to understand that, and we want to recognize that. Same thing kind of here. So this is kind of like doing the long way. The problem is it doesn't work all the time, and that was kind of like doing the derivative the long way. There were functions where we couldn't simplify it. We couldn't do the limit real easily. All right, so anyway, so this, whatever's inside here is a little f. We'll use t's there because we're already using this x. Very important to understand that this x is the same as this x right here, okay? That those two are the same thing. All right, and so what we found out, and looking at yesterday's, then this area function, so when we start talking about, okay, every time we move to a new x, we get a new area, and so if we graph all those different areas, if we get all those different areas, then we end up with this guy here. And the left endpoint was what? That was the plus c, right? That's like the initial condition. That's because we know anytime we do an antiderivative, there's a plus c on there. There's many antiderivatives, and so what determines which one you have, it's the left endpoint. You move the left endpoint, it's the same antiderivative function, it's just a different plus c. It's like an initial condition. It's like a free initial condition, okay? And so we want to take a look at that. All right, so let's talk about number 2. I want to go through the homework. I'm kind of broken. This is such an important section. This 5.2, I mean, it's really like the heart of everything of calculus. I mean, it's the whole, well, it's a fundamental theorem of calculus. I mean, it's the connector between everything that we do. And so conceptually, it's just a really big deal. So you were supposed to, basically number 2 here was supposed to be, as I went around, I didn't always see look like the pictures necessarily you want to have it. This is, we're supposed to basically do what we did yesterday. You're supposed to draw this picture. Here's y equals x, y equals t, okay, from 4 to x, and that's a trapezoid, so we want to write that area. Okay, well, what would be the area? Well, it's 1/2. What's this base right here? That'd be 4, okay? Oops. What's this base on the other side? That would just be x, right? Because it's y equals x. So if your x is there, that's the y. And then what's this right here? X minus 4. Okay? So when we FOIL that, x plus 4 times x minus 4, that's just going to be x squared minus 16. And then we take the 1/2 through there, we get 1/2 x squared minus 8. And so sure enough, that is the antiderivative of this. If you look at the antiderivative, that would be 1/2 x squared plus c. Okay? And again, let's talk about the free initial condition. What's the free initial condition we get in this problem? A of 4 equals 0. That's the free initial condition we get, because right here, if we put a 4 right here for this x, that's the same as putting a 4 right there for that x. The area from 4 to 4 is 0. Okay? We may not know any other areas, but we know that one is 0. So we could have done this, if I do this in red, we could have said, hey, since we know, and that, I mean, even though I'm going to make you, we're going to spend some time doing these area problems like this with pictures, we now know that area is the antiderivative, right? And so that's what we're really going to use. Kind of like when we're doing it the long way, and then we found those shortcuts, right? We did the long way for a while, but then eventually we said we're going to use the shortcuts. X cubed, the derivative is 3x squared. We're going to use that. Okay, well, it's kind of the same thing here. We know the antiderivative of this is 1/2 x squared plus c, right? Plus c. But if we have this initial condition, we can put a 4 in here. 1/2 times 4 squared plus c has to equal 0. That would be 8 plus c equals 0. That would be c equals -8. So we're not surprised that we got the c to be -8 over there. But it's kind of cool that by doing a trapezoid area, by doing this area, it actually comes out to that. It's kind of a neat connection that we're going to keep working on. Okay, so now let's go to that 3 through 11 section. Okay, all right, so you got big A is equal to the integral from 0 to x. Which is larger, a of 1 or a of 5? What'd you say? Why? More what?
There's more space enclosed in this positive.
Okay, what's the word you're going to use? Area. Okay, yeah, space, ground to cover, that's all good. But now, again, several things to check. The reason you maybe didn't think this homework was too hard. I hope. Now, there's a lot of notation, so my guess is there was some of this you were confused on, but you're just not admitting it. But I really want to dig into the ideas because there's a lot of them here. And that's why I want to make sure we understand. Okay, first of all, a of 1 is saying what? What's a of 1? The area from 0 to 1. Because a of 1, a 1 in here means a 1 in here means a 1 up here. So it's the area from 0 to 1. So that is this area right here. That's a of 1. We could actually kind of estimate that, right? Find that value. What's a of 5? That's the area from 0 to 5. Well, like you said, it covers more ground. That's the blue area. Clearly, a of 5 is bigger than a of 1. Okay? All right. What about this one? A of 7 or a of 10? The area from 0 to 7 is all this area plus a little bit of negative, right? What's a of 10? A of 10 picks up more negative area, so its area is actually less than a of 7. Okay? Now, let's talk about this here. Since we know that the area function is the antiderivative, couldn't we have answered this question using chart stuff, not area stuff? Now, I'm glad you talked about it with area, because right now I want us to think of it as area. But I always want to keep going back to it's like slope too, though, right? It's because what does it mean? If f is positive, what's a? Increasing. And if f is negative, a is, right? So, which is bigger, a of 1 or a of 5? This is the f graph, right? It's kind of like having the f prime graph and talking about f, right? So, couldn't we think of this graph as the slopes of the a graph, right? These are the slopes, these y values here. Forget area right now for a second. These y values are the slopes of the a graph. So therefore, what's bigger, a of 1 or a of 5? It's kind of like speed limit law a little bit, right? Not necessarily speed limit law, but the slope idea. So what kind of y values do you have on the f graph all the way to 5? Positive, right? All of these, right? Remember how we used to do that? The f prime graph's positive if it's above the x-axis. Then the a graph, well, we were doing f prime and f. The f graph is increasing. So if the f graph is positive, the a graph has to be increasing, right? So the a graph would be increasing all the way from 1 to 5 because little f is positive. So therefore, which has to be bigger? This one, right? It just goes back to that slope idea. Now, which one's bigger, A of 7 or A of 10? Well, A of 7 is right here. A of 7, okay, if you go to 7, the slope's negative, right? These y values are negative. Little f is negative, and it's negative that whole time. What's that tell you A is doing? A is decreasing. If A is decreasing from 7 to 10, then A of 7 has to be bigger than A of 10. So we could have answered that and this is what we eventually we will do with this for the most part. If you see this on the AP test, if you see this on one of our packets later on, which you will, matter of fact, we've already seen it, I'll show you one maybe later today or tomorrow. When you see this, right away what you'll write down is A prime is equal to F. That's what you'll write down. Wouldn't that be true? This says A is the antiderivative of F, right? That's how you say that A is the antiderivative. If I do the derivative of this, that gives me F. You'll write that down. And right then, once you do that, you have all those connections from the chart that you can use. You can talk about it as area if you want. You can talk about it as slope. They both work. Okay? All right. Why is A of -1 negative? Less than 0. Why did you say that? Because you're going backwards. Because this would be the area from 0 to -1. Well, that's this area. That's this area right here. This area right here normally would be positive, but you're going backwards right to left, so it's actually negative. Okay. Is A of 8 greater than 0? A of 8 would be the area from 0 to 8. Is the area from 0 to 8 positive or negative? Because there's more positive, right, that offsets the negative. But if we're talking about it from slope, it's positive for a long time, including some pretty high y values. So the A graph has to be increasing for a long time, and then after 6, it decreases a little, but not as much as it was. So it's going to be positive. Well, then we also know. Well, I take it back. I know it's going up and then going down a little bit, but is it positive there? Well, that's where we would have to bring in our initial condition. And what's our free initial condition on this one? A of 0 is 0. So we know that the A graph is going to be starting at the origin, and then it's going to be going up for a long time, and it's going to come down a little bit. So it's definitely going to be positive. It's going to be above the x-axis. So that could be another rationale. But I like the fact that you did area. Okay. What about this? What about 8? I noticed some of you had left that blank.
You use the two equations. It's like half of -2 is 0, and A of -2 is negative.
Okay, all right. So on the F graph, the only difference between big F and big A is because they're both antiderivatives, right? The only difference is a different left endpoint, right? Different left endpoint. So like we were showing, that's just a vertical shift. That's just the plus C. But we got to go a little deeper than that, and we got to say, okay, but why do we know C is negative? Now, one way to do it, okay, I like what you said where you could actually do the initial condition. You wouldn't have to do that, though. You could do this. You could say, which is bigger, big A or big F? Okay, well, big A goes from -2 to wherever, right? So let's say I went to here, right? Well, here would be big F, right, of that value. And so that's big F. Big A would only go from here to here, right? Does that make sense? So big A is this one, all right? So are those equal? No. Which one's bigger? F. So for these to be equal, what would you have to do to F? Make it smaller, right? And so the plus C would have to be negative to make that smaller. So that would be one way to do it. But I like what you said. That's more of a plug-in kind of thing. So you could say, okay, the big A graph, you know A of -2 is 0. If you did F of -2, that would equal the area from 0 to -2, which we know is negative, right? Because it would be going backwards. That's what you were saying? Is that what you were saying? Oh, I flipped them around, didn't I? I'm sorry. F of -2 is 0. A of -2, right? A of -2 would go from 0 back to -2. It's above the x-axis, so it has to be negative. So we know that this is negative. So if we just look at those two situations here at -2, this would be 0. This would be negative. So for these to be equal, right, what would C have to be? C is going to have to be negative, whatever that value is. Okay, so that would be a way to explain it as well. Okay, let's go down to this section right here. That's his big F. So this is the same scenario. Big F is the area from 0 to F. Big G is the area from 5 to X. Now we're not using that other graph up there anymore, right? This is a different problem. Furthermore, suppose that little f is greater than 1. Little f is greater than 1. Okay? Explain why f of 7 is greater than f of 1. Somebody want to take a crack at that? What would you say there? Okay? Because of the graph, it looked like this, right? It said little f. It said little f was greater than 1 all the time. So the little f graph has to be up here somewhere. So, right, the farther right we go on big F, right, 0 to 1, 0 to 7, all that, the more area you're going to have. So it's going to be, so that's pretty simple. Okay? Is G of 9 greater than G of 5? Well, what's G of 5?
0.
G of 5 is 0. G of 9 is to the right, and like you just said, since the little f graph's up above, everything when you go to the right is going to be positive area. So when you go to the right of 5, G of 5 is 0, G of 9's got to be greater than. Okay? Now, this also, though, is a speed limit law problem. Okay? Now, again, you probably didn't think about it, but isn't this like saying the slope is greater than 1? Right? So let's just take the f graph. So the f graph, we know f of 0 is 0, right? So if we were going to graph big F, we know that it would hit that point right there, right? And little f is its slope, and it's got to be more than 1. So if you go over 1, you've got to go up at least 1, right? If you go over 7, you've got to go up at least 7. Is f of 7 going to be greater than f of 1? Sure. Now, again, you could also just say, well, little f's positive all the time. So you really don't need the speed limit law, but little f's positive all the time. So therefore, big F is increasing all the time, right? So you could have done it that way and not an area explanation. I'm glad you used area. I want us to use area right now, but I want you to see how it works the other way now that we know there's that antiderivative connection. All right. And then why is big F of x greater than big F of 0? Well, it's kind of what I just said right there. Right? Big F of 0 has got to be 0, and so anything to the right of 0, x greater than 0 there, has got to be a positive area. You're going to gain positive area, so it's got to be, okay, all the time. All right, so we're going to continue on with some of this stuff, same kind of, just get used to the notation of it and all that kind of stuff. You know, you just handed in those packets. I'm just curious here. Probably going to run out of time. I think it might be this one. Yeah. Okay. Look at this was in sample 1. This is one of the problems we'll be going back and doing. And look right here. They give you a graph of little f, right? And look what they say G is. Now G, they did it a little more interesting, but notice how they added that on there, which is just a number, right? That's just a value. But then what does this tell you? That tells you that's an antiderivative, right? And so then right here, where is G concave down? Well, G's concave down when G double prime is positive, right? Well, what would G prime be? G prime would be the derivative of this. Well, what's the derivative of just a number? 0. What's the derivative of this? Little f. Now, would it be little f of t? It'll be little f of x, actually, right? Once it's not in here anymore, then we use x, right? So this is antiderivative. So the derivative of g is just going to be little f, right? That's what you would do in a problem like that. And then, of course, what's g double prime? Bf prime. So they want to know where's g concave down. G's concave down when g double prime is positive. That's like saying where is f prime positive, right? Where is f prime positive? Well, this is f. So we want to know when these slopes are positive. Well, where are these slopes positive? F prime is positive when f is increasing. So really, G is going to be concave down when this graph is increasing. Okay? So you would know that. And so everything in this problem is asked about G, but they give you little f. Well, but we know that connection right there. We know that connection just because we've learned that this area function thing is the antiderivative, right? So we can then we can just use that. So it's just understanding that notation is what you got to know. All right. So moving on. Okay. So get your notes out. Here's what we're going to do. Here's what we're going to do today. And so this is going to be a little more of what we ended with yesterday. And so you're going to finish this in your homework. Then you're going to have a different problem that you're going to mimic this. So when we check homework, well, that's good. I'm glad you got early dismissal so you can use your whole afternoon to work out your homework here for kids. Right? And I'm sure that's what you had planned. That's good. You got extra time. So when I check, because I'm going to want to see pictures, and I'm going to want to see, because what we're going to do is we're going to do this one together. Now this is like number 21. If you look at the assignment sheet, it says 21 through 28 in class. Well, we're going to do some of that up to about number 24, actually, or 23 in class. But 21 is the one that takes all the time. Find formulas for F, G, and H. Then you're going to do 29 through 36 also. And on 29, that's going to be just like 21. It's just you're going to have a different little f to start with. Right? So you have a different little f to start with, but you're going to go through what we're going to do right now. Okay? Now, I will let you shortcut it a little bit on one of them. So here's little f, right? Big F of x is the integral from 0 to x, little f of t. Notice these are all the same except what? Starting point, right? So that's the plus c, we think, is what's going to happen, right? What should happen is different plus c's, okay? So these are all defined up in the directions, big F, big G, and big H. So notice we didn't call them big A. A lot of the time, we still will call the area function big A, but we don't have to, big F, big G. We know they're antiderivatives, so it's not a coincidence we're using big F, big G, big H, right? Okay? All right, so 0 to x. So let's go over here, and let's put an x, right? And here's our area from 0 to x. What shape does it make? Trapezoid, so let's just do it. So we got 1/2. Again, this is kind of like doing derivatives a long way, although I will tell you on our next quiz, I'm not even going to make you go through all of this, right? I did make you do that on the quiz and do the long way of that, but there's going to be some results of this you're going to have to know and be able to do. So going through it is still a good exercise. All right, so what do we got? We got 2. This leg is 2 and won't change. When we slide the x back and forth, right, of course, what is this leg over here? 3x plus 2, right? This leg is whatever the y value is on this function. Well, the y value is that right there, right? This point is the point x and 3x plus 2, right? It's x, y. What? Because this length right here is the y value of this point. And this point is the point xy on this line, right? And so the input is x. So the y is...
So is it only x?
Did you put the x into to get the 3x plus 2 then?
Into 3x plus 2.
Instead of putting a number in,
Thi-
take X.
This is
Wait,
why
where did the 3x plus 2 even come from?
we were given that. We were given that little f is 3x plus 2. See, this is little f right here. So you can think of it as 3t plus 2, right? I could have written 3t plus 2 in here, right? And so I plug a 2 into there, or excuse me, I plug a 0 into 3t plus 2, so I plug a 0 into there, I get 2. I plug an x into there, I get 3x plus 2. It just, I mean, if I have a parabola, Emily, if I have a parabola that's y equals x squared, right? What is this point right here? It's xy, right? Or another way to think of it is x squared, right? The y value, this y value right here is x squared, right? And so that's what I want. I want to know this y value because that's this base of this trapezoid. Okay, so I got 2 plus 3x plus 2, and then times the height of the trapezoid, which is this right here. What's that? X minus 0, which would just be x, right? X minus 0 would just be x. Okay, let's distribute that out. So we get 1/2. This would be 3x plus 4, and this would be times x. So let's just distribute the 1/2 x can go together. So 1/2 x times 3x, that'd be 3/2 x squared. And then 1/2 x times 4 would be 2x. So we just found that big F of x is equal to 3/2 x squared plus 2x. Agree? Now, isn't that the antiderivative of little f? Right? Not a surprise that antiderivative, raise that up to a 2, divide by 2, that'd be 3/2 x squared. Antiderivative of 2 is 2x. Plus c, it turns out our plus c must be 0 in this one. We'll get to that in a minute, right? Remember, we got that free initial condition, but I'm not going to talk about that just right yet. Okay, now we're going to skip to h. I'm not going to do g. We'll just cheat on g because we know it's, you're right, we know another way to get these things, right? It's with antiderivative. So let's just do h now. So let's do h. So h would be from -2. So -2 would be over here. Okay, so now that's going to be interesting because that's going to be two triangles, right? The area from -2 to x, that's actually going to be two triangles, right? And this crosses here at -2/3. I just set this equal to 0 and solved it, right? So I know that line crosses at -2/3. So what's my blue area? Well, it'd be this triangle. And now when x slides back and forth, now remember, yes, I could take this x and I could slide it way over here like I was doing in those other pictures, but that just makes it more confusing. It still works, but we don't want to mess with it. Let's keep x over here. So when I slide x back and forth over here, this piece right here won't change, right? That piece of area will just be the same. So what is that? Well, that's -2/3 to -2. So what's that? 4/3? That'd be 4/3, right? And then what would this be right here if I put a -2 into this? This would be -4. So this triangle right here would be 4/3 times 1/2 times -4. And it actually is times -4 because we want that to be negative area, right? This is negative area right here. This piece is negative area, right? So we'll go ahead and put that. So that's, what is that? -16/6. What would that be? -8/3. I'm just going to reset. Put -8/3. Okay. So that's -8/3 plus, and now I have a triangle. So that'd be 1/2, right? Now what's this base of this triangle right here? That would be x plus 2/3, right? Because it'd be x minus a -2/3, right? So it'd be from here to here, that would be just x minus that, x minus -2/3, okay? And then what would be this height right here? Oh, we already said that's 3x plus 2, 3x plus 2, okay? All right, so we need to FOIL this, and then we got a 1/2 there, so let me write my -8/3 plus, now let's FOIL this. This would be, so I still have my 1/2 here. So I got x times 3x, that's 3x squared. I got my outers, that'd be 2x. I got my inners, what's 2/3 times 3? That's also 2x, right? So outers 2x, inner's 2x, so that'd be 4x. And then 2/3 times 2 is 4/3. So I FOIL all that. Now I need to distribute my 1/2 through there. So I would get 3/2 x squared plus 2x plus 2/3. Now I can add the 8/3. What's negative 8/3 plus 2/3? Negative 6/3, which is negative 2. So at the end of the day, this ends up being 3/2 x squared plus 2x minus 2, and that's big H. And look at that, just what we were hoping for, right? It's the antiderivative. It's the antiderivative of little f over here, right? So don't get too hung up in the mechanics of this trapezoid and all this stuff in here. I mean, that shouldn't be that hard. I mean, this x minus this is what that is. That's that length. You know, they're even getting some fractions, and it can get kind of messy. But at the end of the day, what you really need to know is the big picture here. The big picture is these are all antiderivatives of little f. Little f is this line. The antiderivative is that. Different left endpoints give you different c values. Now, we can check this out. We knew, what was our free initial condition on h? We knew that h of negative 2 was 0, right? So an alternate way of doing this, right, and a better way, and the way we will do it later on, right, as we go forward, is we'll just say, oh, okay, antiderivative of this is 3/2 x squared plus 2x plus c. When I put a negative 2 in there, I get 3/2 times 4. 2 times negative 2 is negative 4 plus c, that's got to equal 0. 3/2 times 4 is 12/2, that's 6. 6 minus 4 plus c equals 0. 6 minus 4 is 2 plus c equals 0. So c would equal negative 2. Sure enough, c was negative 2. Right? So that is how we would do these. We would say, aha, h is the antiderivative of that. We get a free initial condition. We can figure out what it is. Matter of fact, let's do that for g right now. Let's just kind of cheat on g. We know g is going to be what? 3/2 x squared plus 2x, right? We know it's going to be the antiderivative of that. So raise that up to a 2, divide by 2. 3/2 x squared, the antiderivative of 2 is 2x, plus some c. Our free initial condition is g of 1 equals 0. That's our free initial condition, because if you put a 1 right here, if you put a 1 right here, that's like putting a 1 right there, and that's the area from 1 to 1. So g of 1 is 0, so we can put a 1 in there, so we get 3/2 times 1 plus 2 times 1 plus c has to equal 0. So what is that? That's 3.5. 3.5. So 3.5 plus c equals 0. So c would equal negative 3.5. Did I do that right? Oh, 3.5. Okay, so c is negative 3.5, isn't it? No, 3/2 is 1.5 plus 2. That'd be 3.5, wouldn't it? Okay, so c is negative 3.5. So we know the g function would be, I'll write it down here, we know the g function would be 3/2 x squared plus 2x minus 3.5. That would be the g function. So all three of those are antiderivatives of the original little f, right? The first, or f and h, I did by doing the actual area of the picture. G I did kind of by our antiderivative, because we've learned, we've figured it out in the last 2 days, and oh my gosh, yeah, it's antiderivative. Now, here's why the area, well, you guys tell me, why doesn't the area way work that much? Why isn't the area way the way to do it all the time, besides being long? Yeah, I mean, only because this is a line equation does it give us shapes we can use, right? If I give you the sine graph, if I give you sine as little f, we're not going to be able to do, you know what I mean? We won't be able to do that area. There won't be an area for what we can do. So the fact, but this, I just think this is cool to do because it reinforces, number one, It reinforces for us that this is an area function. It reinforces this idea of the free initial condition, and it's some good algebra practice, right? But it just, and then at the end of the day, it's just cool to see the antiderivative come out at the end when we're done. Okay, and it should. So you're going to have something very similar to that to do. And so now, if we look at the questions, so on page 320, if you to open your books to page 320 here. Let's. Okay, so on 320, problem 21. So there's these exercises 21 through 28 that all go together. Okay. Now, so find formulas for F, G, and H. So all that work was number 21. Okay. 22, find a number C such that G is equal to F plus C. Well, if you look at G, when would these be equal? When would G equal, what is it, F plus C? Well, for these two to be equal, you would have to do what to F? You'd have to take away 3.5, right? You need to stick a negative 3.5 on it. So C would be negative 3.5, right? So once you're done, you can answer these questions pretty quickly. Find a formula for big F minus big H. Well, what's going to happen if you take big F and subtract big H? Positive 2, right? Because big F subtract big H, 3 halves x squared minus that's gone, 2x minus that's gone, and then 0 minus negative 2 is going to be 2, right? All that's going to be left is 2. Just another way of saying it's kind of like this. If G is equal to F plus C, if you do G minus F, you're just left with the constant, right? Those are just different ways of saying, hey, big F, big G, big H are the same except for the constant. They're the same except for the constant, right? They're all antiderivatives. That's what that's meaning.
What would your formula be? Is it just,
2.
that's just what you see?
That's all you have left. If you do big F minus big H, you'll get 2. So your formula would be 2. Okay. Where is big F increasing? Okay. So we look at big F. So let's think about it in terms of area. Where is big F increasing? F is from 0 to x. So when let's say we start right there at 0. Now it turns out we don't have to start at 0, but a big F was red, so let me go to red. So let's start right here. So when I drag the x this way, is it increasing? Big F would be increasing because I'm picking up positive area. Now this is where it gets a little tricky. I want to make sure we understand this. We talked about this in the other class, but not in here so much. When I drag this way, I'm going to be picking up area. So my big F graph is going to be going up, 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 right? And I'm also picking up bigger chunks of area. So it's going to be going up like that. What if I drag it back this way? What's happening? Aren't I picking up? But what kind of area am I picking up? No, because I'm going backwards. Okay, I'll tell you what the best way to see that is probably go back to this. Okay, so let's say I'm starting here. Let's say I'm starting right here at Z. Let's say I'm starting here. So right now, when I go this way, I'm picking up what? Positive area. So clearly this graph's going up, right? But what happens when I get on this side of it? What am I picking up? I'm picking up negative area. So what's my area graph doing? It's going down. But even though it's going down, do we call that decreasing? Is this part of the graph decreasing? No, it's increasing because we're going backwards, right? I mean, so on this picture, so when I start dragging back this way, when I start picking up this area, this negative area, what's it doing? It's just making this graph continue to go down, right? Now, what happens right here? I start picking up what? Positive area, which means this graph would start going up. But really, that's what? That's really decreasing part of the graph, right? So where did the increasing and the decreasing start? Right there. Well, that's what we know from our chart, right? When the little f graph is below the x-axis, this graph should be decreasing. When this graph is above the x-axis, it should be increasing. it gets back to something I said way at the beginning of the year where I said there's two ways to increase. Be positive and get more positive, or negative and get less negative. Those are both ways of increasing, right? So it turns out, and again, it goes back to this picture. That's why when you move this left edge, this doesn't change where the chart stuff, right? Does the concavity change when I move this? Does the increasing, decreasing places change? No, it still is decreasing till here and increasing till here, right when this crosses. See, if I move this over here, okay, so now think about it. When I have my left edge here, right now I'm losing positive area, right? Would you agree with that? See, the yellow is going down, so I'm losing positive area. So this is going down, which really is increasing. But once I cross this, I quit losing positive and I start what? Gaining negative. Aren't those two the same thing? Losing positive and gaining negative are the same thing, right? So that's why this graph is still increasing. So that's why it doesn't matter where this left edge is. Let's move the left, oops, that's right edge. Let's move the left edge over here. So right now I'm losing positive area, right? So this graph's going down. Losing positive area, losing positive area, losing positive area. Now what am I doing? No, I'm not gaining. Look at the yellow. The yellow's disappearing. I'm losing negative area, and it's still negative area because I'm going A to X, right? So I'm not going backwards right now, right? I haven't crossed my left endpoint yet, right? So right here I was losing positive area, so this graph was going down. But right here, what happened? I started gaining, or excuse me, I started losing negative. Well, what's losing negative? Gaining, right? That's gaining positive. So I was losing negative area, so this graph started going up. Right now, before, when I had the A over here, when I was sweeping here, I was gaining positive area, right? Right now, I'm losing negative. But see how they're the same thing? They're the same thing. So when you move that left edge, it just takes you to, instead of gaining negative, you're losing positive. They're the same thing. So right now, I'm what? I'm losing negative area, right? Losing negative area, which is like gaining. And then what happens here? I'm gaining positive area, right? Because this is now backwards, but it's below, so I'm gaining positive area, so it's up here. So here I was losing negative, got past one instead of gaining positive. So it doesn't matter where the left edge is as far as the increasing, decreasing stuff, right? So I'm not sure that's that big a deal. I think it's important to understand that and make sense of that. But the bottom line is, when it comes to the chart, when it comes to a question like where is big F increasing, big F is increasing from negative 2/3 to infinity. Would you agree with that? Big F is increasing from negative 2/3 to infinity. Why? Because that's where little f is positive. Now, what if the question was, where is big G increasing? What? Okay, we just said, listen, big F is the antiderivative of this, which means this is a derivative, right? When this is positive, this is going to be increasing, right? When little f is positive, big F is going to be increasing. Little f is positive from negative 2/3 to infinity, right? From right here, right on. So big F is increasing from negative 2/3 to infinity. Where is big G increasing? Same place. That's the point, right? That's the point. It's still, big G is increasing when little f is positive. When's big H increasing? When little f is positive. Negative 2, right? It's the same place. Because they're all antiderivatives. All they are is vertical shifts, right? They're just vertical shifts. So where it's increasing, that vertex down here where it starts increasing, it just shifts up and down, right? It's still increasing from there. Concave up, concave down, same thing, right? All the chart stuff, when you shift a graph up and down, none of the chart stuff changes, right? We talked about that before. So you change left endpoints, right? It's easy to get hung up in that area argument and think it's different, and it's not. And that's what I was going through just a minute ago with the losing positive and gaining negative and so forth, right? That's all that changes, is the way you're saying it with the area, okay? So people get really hung up on that left edge. When that left edge changes, yeah, you get different areas, but it doesn't change the area function as far as where it's increasing, decreasing, concave up, concave down, all that stuff. Okay? All right. Very important. So that, I just did 24, we just talked about 24, but that's part of your homework now to answer those questions, right? But they're basically chart questions, right? But I would like you to think of them in terms of area. Try to think of them in terms of area, okay? That way. All right. So, last thing for your notes. So, to summarize on this, I've said it 100 times now in the last 2 days. What's the connection between A and F? A is the antiderivative. Here's how I want you to start saying it. I want you to say that right there. I want you to write it like that. Now, you can write it out. A is the antiderivative of F, but that's how you say something is the antiderivative. Something is the antiderivative. X squared is the antiderivative of 2x. Why? Because when you do the derivative of x squared, you get 2x, right? That's why something is an antiderivative. It's an antiderivative because when you do the derivative of it, it gets you back to that function, okay? So A is the antiderivative, so the connection between A and F is that if you do the derivative of A, you get little f. And it would be little f of x, not t. Okay, so this is called the Fundamental Theorem of Calculus Part 1. Okay, there's actually 2 parts of it. This is basically what I just said, but in more formal language. Didn't we just say on the other page that the derivative of A is little f? The derivative of A is little f. Well, all I've done here is put, the derivative of big A. The derivative of big A is little f. So what I've just done is put big A in. I just put big A in, which is that area function. This is the Fundamental Theorem of Calculus. Now, it looks really confusing, but all it's really saying is the derivative of the antiderivative gets you back to what you started with. But notice it's little f of x. Inside here, it's little f of t. But when it comes out here, it's little f of x. That's very important. Remember, that's what happened to us. When we wrote our area functions, when we did our trapezoids and we wrote those, they came out as little x. As a matter of fact, it goes back to what Emily said. Emily said, how come that y value is 3x plus 2, right? The function was 3t plus 2, right? Well, because we put an x in, and that edge became 3x plus 2. And so when we did our areas with those trapezoids, we ended up getting big A of x. It had x's in it. When you do the derivative of it with respect to x, you get back to, right? So if we would go back to this page, and do the derivative of every one of these, what would we get? We'd get 3x plus 2, right? The plus c's would disappear. Every one of these, when we do the derivative, would get us back to little f of x. Not little f of t, it was little f of x, because we ended up with x's in there. Now, I will tell you, on our next quiz, there's going to be one question on there that should be the easiest question of all. And it's going to be something like this. That's going to be the question. What's going to be the answer? Max said this. If you write e raised to the sine of t cubed, you will miss it. Jesse, what is it? It's got to be x. Yeah, that's what I'm just going to say, right? That's what I'm just going to say. In here, it's t. When it comes out, it's x. But you haven't do anything because what's it saying? This here, and does the 3 matter? The 3 is the plus c. What happens when you do the derivative? The c goes away, right? So big at that other page, big F, big G, big H, it didn't matter, right? When we do the derivative, we get 3x plus 2 every time because the c goes away, right? So this will be some antiderivative. Do we know the antiderivative of that? I'll purposely put something in here. We can't do the antiderivative of that. There's no antiderivative of that, okay? We can't do that. We don't need it. In here's the antiderivative. This says do the derivative. It gets you right back to what you started with, except it doesn't have a t and it's got an x in it. That's all you do, right? But, so fundamental theorem part 1 is not a real useful theorem for anything, but it says and what we've been talking about for 2 days. It says that the area function is the antiderivative. That's what it says. It says the area function is the antiderivative. Okay, so your homework is you're going to pick up where you left off. We stopped at number 11, so we're going to go 12 through 14. Then I did 21, 22, and 23 with you, so you're going to go 24 through 28. So that'll just continue that work we were doing in our notes there. And then you're going to do 29 through 36, which is essentially 29 is just like 21, the one we did together, except it's another little f. It's a different little f. So you're going to draw that picture, and you're going to have all this work for number 29. And then the other questions are the same as 21 through 28. Okay? That's what I'm going to be looking for, especially.
Any shortcut on, is there 3 equations?
There's 3, and you can do the shortcut on one. Do F, do H, do that shortcut on G with your free initial condition. Yeah.
Why is it not dy?
Well, because the D just means this is the Y.
Because of the t.
It's the derivative of this with respect to X. Remember, we used to do that. When we wrote our derivative rules, we did this. We wrote it like that. This says the derivative of X squared with respect to X. So it's like we're taking the Y and replacing it with that. That's what it means. So I could have stuck this up top with the B, but it just uses it right now. That's what it means.
Yeah,
Calculus.
Woohoo!
Yippee.
Is today gonna be as exciting as yesterday?
It's still pretty exciting. I mean, I think. I don't know. That's me.
Are we actually doing all those problems in class?
What?
Homework? Like the homework sheet said in class.
Oh, yeah, no. Yeah. You mean for today's homework? Some of it. Yeah. Yeah, we are.
We do all this.
Don't worry, there'll be plenty later.
Yes.
It's game day, boys.